All right, guys, I wanted to go over a couple of the multiple choice that deal with rotational kinematics problems. So it says that a turntable that's initially at rest is set in motion with a constant angular acceleration alpha. What is the angular velocity of the turntable after it has made one complete revolution? One revolution is 2 pi radians. That's going to be my theta minus theta naught. And I'm going to say that omega squared equals omega naught squared plus 2 times alpha theta minus theta naught. And so omega is going to be equal to the square root of 2 times alpha theta minus theta naught, because this is 0. It's initially at rest. And so this is going to be the square root of 2 times alpha times 2 pi, which is choice C. Clear the ink. A wheel of 0.5 meter radius rolls without slipping on a horizontal surface. The axle of the wheel advances at a constant velocity, moving a distance 20 meters in 5 seconds. The angular speed of the wheel about its point of contact on the surface is. Constant speed tells us it's just distance over time. This is going to be 20 divided by 5, or 4 meters per second. Angular speed is velocity over radius if it's non-slipping. Only if it's non-slipping. And so this is going to be 4 meters per second divided by 0.5 meters, which would be 8 radians per second. So that's only a non-slipping angular velocity. A disk is free to rotate about an axis perpendicular to the disk through its center. If the disk starts from rest and accelerates uniformly at a rate of 3 radians per second squared for 4 seconds, its angular displacement during the time is 4 squared would be 16 times 3 is 48 divided by 2 is 24. And all of these were straightforward. This next one isn't. That's why I felt like I needed to do this on here, because it's going to take some space. All right, a block of mass M is placed against the inner wall of a hollow cylinder radius r that rotates about a vertical axis with a constant angular velocity omega, as shown above. In order for friction to prevent the mass from sliding down the wall, the coefficient of static friction mu between the block and the wall must satisfy which of the following inequalities? All right, so first, free body diagram. There's a normal force towards the center. There's a force of friction up. There's a force of weight down. In the y direction, F net is equal to 0. So friction is equal to mg. In the x direction, F net is equal to mv squared over r. N is equal to mv squared over r. We have a non-slipping situation here. I'm going to get angular velocity in for regular velocity. So angular velocity times r is equal to v. So I'm going to plug this in for v squared, and I'm going to get that n is equal to m omega squared r. So we'd have omega squared r squared, and it would cancel one r out. So this would be equal to mv squared over r. I'll write it up here because that is not. So I have m omega squared r is equal to n. I also know that friction is less than or equal to mu n. So n would be greater than or equal to F over mu. And so I'm going to say that F over mu is less than or equal to m omega squared times r. I also know that F is equal to mg. And so I have mg over mu is less than or equal to m omega squared r. And look at that, I can cancel a whole mass out. Wow. I'm going to multiply both sides by mu and divide both sides by omega squared r. So over here, I'm going to have mu. Over here, I still have a g, and I'm going to divide by omega squared r. And so mu is greater than g over omega squared r, which is b.